All right, so we're on to this next slide here where previously we discovered or determined that the average power of this circuit that we've been analyzing is 50 milliwatts, right through the middle. Kind of plotted that here just as a part of my figure, but we're basically going to recalculate the average power, but not using this integral of the average value of the signal that we found in the time domain, but rather using this function here, this formula that says that we can basically take the average by just multiplying the two RMS values together of the current waveform and the voltage waveform. This should make sense considering we said that the RMS value of a signal was the DC value that delivers the same amount of power to a load as the AC signal itself. So these two IRMS and VRMS are basically the DC equivalent signals for the voltage and for the current. If we multiply them together, we get the average power. It's pretty similar to just P equals I times V for the DC case, but these are basically DC equivalents for our AC signals. And so you might be thinking, oh boy, we have to find the RMS value of the current and the RMS value of the voltage. That's even more work than what we did previously. But recall that we found already, if I go back to our RMS slides, we've already discovered the RMS value of a sine wave, any sine wave. This solution is general. Any sine wave, if we know the peak value of that sine wave here, which we do for our voltage and our current, we can just say that the RMS value is the peak value divided by the square root of 2, or 0.707 times the peak value. So let's go back to where we just were. We are here. And let's re-establish ourselves. Let's get our voltage and our current and all this that we've been looking at. So let me take that and put it here. Do I have room? Yeah, I have room. Okay, perfect. So if we want to find VRMS, we know that the voltage is just a sine wave, so it has a peak value of 10 volts. So we can say that the RMS value is going to be 10 divided by the square root of 2 volts, RMS, which is the value that we got previously from our general sine wave RMS derivation. For current, it's going to be the same thing. It's going to be 10 divided by the square root of 2, but in this case, it's going to be milliamps RMS. And so when we go to find our power average, we can just say that our average power is 10 divided by the square root of 2 volts RMS times times 10 divided by the square root of 2 milliamps RMS. And we get that our average power is 10 times 10 divided by the square root of 2 times the square root of 2, which is 100 divided by 2, or 50 milliwatts, which is exactly what we got previously. Okay, so that is a very easy way to calculate the average value, which we calculated here, obviously doing some integration, and we took the integral or the average value of our time domain expression for the power, which is perfectly valid, but this is just another even easier way to solve for the average power, especially when your signals are sinusoidal and especially when you have a purely resistive load. This is where it becomes important that the load is purely resistive, because if the load is not purely resistive, there's an added term in this expression here that we need to take care of, and we're going to see that in the future videos. I'm going to get to the point where what if the load is not purely resistive, and we're going to show what happens, and we're going to show how this formula here is actually just a special case of the general formula. But for the case where the load is purely resistive, you can always use IRMS times VRMS, and because we already know how to find the RMS voltages, the RMS values of sine waves, it's quite trivial to determine the average power using those signals, right? 10 over root 2 times 10 over root 2 is 100 over 2, which gives us 50 milliwatts, okay? Of course, this is saying that volts times amps RMS is still just watts. The RMS is just there to indicate that we've taken the RMS value, but we still have units of volts, units of amps, and so we get watts, and then the M is still indicating that we are at the milliwatt scale. Okay, so I'm going to go ahead and end this video. I think in the next video I probably have an example problem or something. Let me take a look. Yeah, so we'll do an example problem with the resistive load. We'll find the instantaneous, but we've kind of already done that, but I guess I'll do another one real quick. And then when we finish that example, we're going to take a look at the case where the load may not necessarily be purely resistive. We end up with a phase shift and all sorts of interesting things happen. Okay, so and that's actually the much more common, much more practical thing to know. This is all prerequisite knowledge for what's coming, but it's much more practical to understand how to do this when the load is not purely resistive, because in any practical circuit, you're going to have to deal with some parasitic inductances and capacitances, and there's not always a purely resistive load. Almost never will you have perfect power factor, which we haven't talked about yet, but we're going to go ahead and end this video, and we'll do the example, and then we'll get into that stuff in the future. Okay, so I'm going to end this video right here.